We are at a descriptor SIFT. We are talking about how to arrive at a descriptor of SIFT. And I think I just started talking about it during the last class. So I said that this is a 128 dimensional vector. And it involves a bunch of steps. Right. So first of all, so around the interest point, at which we have already seen how to arrive at the interest point, and there is a definite dominant orientation. So around interest point, a 16 cross 16 grid is chosen. Now this grid, okay, that doesn't mean it is no. So the grid size itself, whether it involves 16 cross 16 number of the pixels or whether it involves more number of pixels, depends on the scale. Okay, now this is somewhat like a kind of hyperparameter. Okay, so it's not very clear. I mean, nowhere do they tell us to what should be the scale. I mean, right. So the only thing that we know is if you go up the scale, then this area will also increase. Okay, so maybe right, you can just kind of make it a function of sigma. Right. The simplest thing that you can do is multiply it with actually with the kind of value of sigma that you have. Because I've tried looking for this, but that specific information, right, even in the Octave or the OpenCV implementation, nobody tells you exactly what is that. What is even the original paper doesn't say. It just says keep it as a function of the scale. Okay, I think it doesn't probably, it's not very sensitive to that. A 16 cross 16 grid is chosen. So grid, okay, this is not like pixels. And the gradient norm and orientation, this the gradient norm and orientation are found for each of the pixels within that grid, found for each of the pixels. Okay, then there is a Gaussian weighting that is done, okay, on this norm, because something that is far away, because this grid can also be big, right, because it kind of changes with the scale, by which I mean that the extreme point at whatever scale you found. Okay, so by the 16 cross 16 grid, we mean that at that scale, right, at that scale it could be a large region, are found for each of the pixels. And okay, yeah, I think I probably already said last time, to achieve rotation invariance. Okay, for rotation invariance, you kind of recompute the angles with respect to the dominant orientation, which is the orientation of the key point with respect to the dominant orientation of the key point. Orientation of the key point. Then you do some kind of Gaussian weighting now. So the norm of the gradient is actually Gaussian weighted now. The norm of the gradient. So what this means is that depending upon how far away you are from the key point, you sort of reduce the what do you call the the weight the value of the norm. The norm of the gradient is or the strength of the norm of the gradient of the norm. Norm of the gradient. To achieve rotate their angles, the norm of the gradient is Gaussian weighted. Gaussian weighted. Again, right, I think there is this one is something like 1.5 sigma is what they say. Okay, this is again a hyperparameter. So if you are at that scale, right, then you take a Gaussian weighting of 1.5 sigma. Again, I am not going to write it down because these are all, I think, different implementations claim different things. Somebody will say 2.5 sigma. They say Gaussian weighted by the, and again, okay, this weighting depends on the scale. Depending on the scale, well, not exactly, right, because this is like 1.5 sigma, right. So it's not. So let me write this as, I'll just write approximately 1.5 sigma. This one. This grid is dependent on the scale. This is dependent in the sense that it's already like 1.5 sigma, right. So this one is what is dependent on the scale. It's Gaussian weighted by the this is distance of a pixel to the SIFT point. See, that's also the reason. This is also the reason why, for example, right, generally, if you implement a vision code, right, seldom will you find that you can take something off the shelf and use it. I mean, I don't know how many of you have tried it out. This was also the reason why why it took a long time, in order to make these things really robust and all. It's all these, even though the theory may look good, but then in a practical implementation, right, when you actually use it, when you cannot directly use, directly take it from a MATLAB code and start using whatever images you have, you always invariably have to tweak something. Yeah, this has always been an issue. This is unlike your, a communication or something, right, where, things are kind of well laid out, right. So, that's always been an issue, but now with these deep networks and all, the robustness has gone up like, multifold, but this traditional methods, right, there's always been, somewhat of a, somewhat of an issue, a ticklish issue. It's not something very serious, but yes, but these things matter, because if you think that, I can just write, take an image of this room and then I take another viewpoint, I can automatically match, I can run, SIFT. Now, very likely that simple problems that you can solve, but in the moment, right, the problems become more complex, it's normally not true that you can take something off the shelf and use them. So, you will invariably have to tweak something. The 16 is then divided, the 16 cross 16 grid is divided into 4 by 4 cross 4 blocks into 4 cross 4 non-overlapping blocks. Non-overlapping blocks. So, it's like saying that, right, you have a 16 cross 16 grid. So, you do it like 4 cross 4, right, non-overlapping blocks, divide them, and then an 8-bin histogram. By the way, this orientation based histogram that we are creating, right, this is itself is actually, in the next class when I talk about hog, okay, that is actually based on this kind of an idea only. So, an 8-bin orientation histogram, quantized at 45 degrees. Again, that's what I'm saying, right. So these are all things that you may have to tweak, okay. But of course, the fundamental sort of a descriptor is this, is computed for each 4 by 4 block. Okay, so then what this actually means is that you've already weighted the norm and all, right. So, for example, if you're at the center, then something far away from the center, it's this one, the gradient strength has already been sort of weighted down, and now we're right within kind of each of these blocks. Now we are actually creating these orientation bins, which is the same way, right, that we said. So, for example, so 45 degrees means you'll have kind of say how many bins you will have, 8 bins, right. So you have an 8-bin histogram. And then right now you start to sort of see, right, which, so wherever if some sort of a pixel has a for a certain orientation, it has a certain gradient norm, you actually put that into that bin, and then you add up, right, so that you get again a sort of 8-bin orientation histogram for each, and there are of course 16 such blocks, right. It's computed for each block, for each 4 cross 4 block, for each block. So, and since there are 16 such blocks, and this ordering and all is important, okay, the way you order. For example, see, what you do is you do simply this one, a concatenation. So, for example, you have an say 8-bin orientation histogram, right. Let's say for this you have an 8-bin, for this, right, you have an 8-bin histogram, right. Then when you actually concatenate them, you got 16 of these, right. So, you concatenate them into one. That's what I mean by a 128 dimensional vector, right. So, you have to concatenate them. So, when you concatenate, you concatenate the same way, right, every time, okay. That's so you can't just change the order. So, since where is that? So, thus we get okay, since there are 16 blocks, you get a 128 dimensional feature vector, or a descriptor in this case, 128 dimensional SIFT, this one, a descriptor. So, what this means is that, right, this is able to extract information in and around that feature point that actually explains that region. okay, explains that region in a manner that that for example when you match, right, if you, so the whole idea is that if you directly try to match intensities, right, it won't simply work, okay, right, that's the whole idea behind going after features and all, right. If you have just two images, you can't simply take the image intensities and start matching, right. So features are far more robust because you are kind of extracting a lot of things that you believe makes for gives room for invariance for a lot of things. Get a 128 dimensional descriptor, which is the, okay, now and then of course this is further normalized to to actually unit length. This further normalized, right, prior to normalization, clearly, I mean, you know that there is a rotational invariance because of this, right, because of the rotation where you kind of recompute the angles, right, with respect to the dominant orientation. Therefore, rotational invariance you can see is already inbuilt to the into a descriptor. The other thing is scale invariance, we know is already coming because of the way you actually solve for SIFT itself, right, solve for the features, and therefore, right, and therefore, I mean, right, so you can see that the fundamental things that you want out of this in terms of the invariance, for the geometric invariance, right, it already satisfies things that you would want it to satisfy. In addition, for the photometric part, right, this is further normalized. Of course, translation variance is obvious, right. So this is further normalized for photometric variations or intensity variations. Okay, this is further normalized to unit length for photometric variation. So it's like saying that if you had a contrast increase, right, for example, if you had like A times I. Of course, if you had an addition, that anyway it takes care of because you're doing a Laplacian, which is like dog, which is like a derivative. So any addition is okay, you can handle, no problem. But if there is a contrast increase, right, let's say you have some like multiplication of A, right, then the idea is that, right, I mean, because you have gradient will also get scaled by that factor. If you simply normalize it out, right, then it shouldn't matter when you actually match. But this is only if the illumination is sort of uniformly going up, right. For non-uniform illumination, which you can have, for example, non-uniform, by which you mean that suppose I take this image, right, so whatever is falling on this side is very bright, right, and then that side is not so bright. So you have a local sort of illumination which is very high. So in such cases, right, this cannot completely handle it. But then what they do is, they normally sort of put a cap on how much, for example, after you normalize, right, so you have this 128 dimensional vector, right, so which you have kind of say, right, which you have done a normalization. Now, which means that if you sum up all these values, right, it will be equal to 1. So what they do is, the maximum that they allow is actually 0.2. This is again an implementation thing. So the value, right, cannot kind of say exceed 0.2. If something exceeds 0.2, then it is frozen to 0.2. You don't allow it to go beyond that, simply because it could be happening because of some say non-illumination variations, and then of course you'll have to say renormalize. That you know how to do, right? I mean, it's like saying that you freeze everything and then you add up all the quantities, right, and then you simply scale every number by that sum, so that the sum again sums to 1. But now you have sort of capped the kind of say contrast sensitivity. It's all this is more like empirical. Okay, this is not a strict theoretical result that if you do this then you can, because non-illumination variation itself, it can be of different types. There could be specularity and also it's not to claim any of that. These are all things that they found out, right, works in practice. And the interesting thing is, even though right, strictly speaking, this is sort of, this is not even meant to handle affine transformations, right. But in reality, right, people have found that this works extremely well. I mean, under many conditions. Okay, in fact, you should do this. Just take right, go outside wherever, in a hostel or wherever, right, inside the campus, wherever you are. Take your cell phone. Take, let's say, right, 2 images of a scene. Today you take one. Tomorrow again, when you go back, right, take another image. Don't take from the same viewpoint. Try to see, right, I mean, how many matches you get, and take any SIFT off-the-shelf code and run it. Of course, see, there were further further improvements over the basic SIFT. There is even something called an affine SIFT and all, that is basically tailored to handle affine variations and all. We don't actually go into that in this course, but the point is, even the basic SIFT, right, you will be surprised. You should even try something like day and evening. Even try that, right? Take something that is like bright, in the morning, and then come back in the evening, 6 o'clock. Don't take them very dark or something, but maybe, right, this one, a dusk time, right, you take, and then you should again run and see, right, you will be actually surprised that it works so well, and it's very fast, the implementation and all, right, and you know, that slide, it doesn't have very good examples, but I think you should try it yourself. Why should you have to accept, right, what I show here, right? Why don't, because these are things that you can try yourself, right? It's very easy to you're not implementing it anyway. You're just taking an off-the-shelf code, running it on images just to see whether the comparisons are good, whether the matching is good. Sometimes you won't be able to match, but then this would have matched it well. I think I showed a Mars image, remember? But it was very difficult for us to tell that there is a match. Okay, so much for SIFT. Okay, let's go to the next one, which is called SURF. SURF, right? This was that was 2004, right? So this is, I think, 2006. This actually came as an improvement to SIFT. This came as an improvement over SIFT. Basically, many of the ideas are borrowed from there. The authors are not. It's actually a different. These are different authors. So this guy is some Herbert Bay, and Lakwan Goul is. So this group is very good. Okay, this is headed by this chap. So 2006. Okay. So what does SURF stand for? It stands for let's speed it up. Robust features. Okay. And the main idea is to speed up things. Okay, I mean, even if it comes at some cost of at the cost of making some approximations. Okay, and it actually runs very similar to SIFT, but then the idea, right, that they've used is actually very nice, and it's very interesting, right, how they solve this problem. So we'll see. Okay, so improvement. So basically, you know, it's as an efficient alternative to SIFT. In fact, right, this implementation also is available. Okay, if you can even try this in addition to SIFT. But of course, you know, you won't notice the speed difference if efficient alternative to SIFT. So the main thing is, right, instead of trying to rely on a Gaussian function, I mean, I told you, right, I mean, I think in one of the classes I told you why, let's say, a Gaussian has been the ideal pick for, let's say, several reasons. One is, of course, all the math that showed, you know, how you can pick, you know, from a log, the extreme and all that. But in addition to that, I also said, right, if you scale up, the lower features will start to go away, only the coarser features remain, no artifacts get introduced. Actually, I mean, if you really read about it, right, the actual theory says that for a lot of 1D, right, this has been proven, but for 2D, it doesn't look like, right, there is so much of, you know, sort of a theoretical support. People just believe that whatever is happening in 1D should also most likely happen in 2D. So the argument, right, that these authors make is that, you know, because of the fact that, right, it's not yet completely proven that, you know, that a Gaussian for a 2D case is still the best. So they go ahead and approximate. They say, okay, fine, right, let me do something else. And the process, right, it's not like a bad approximation, but it's a very smart approximation. And they actually show that, right, if you were to solve it using what are called box filters. So box filters, the idea is to use box filters as approximations to the Gaussian derivatives. Right. Now you may wonder, so box filter is typically like what, I mean, on all ones, right? So something like this. I mean, typically, right, by box you mean that it's a kind of, you know, a contiguous array of numbers, right? So you can have something like what, this is like 4 cross 4, so I may have like 1 by 16 all ones. Right? This is actually a box filter. And you might wonder, right, I mean, you know, why such a thing why does it even make sense, right, that you have something like this, you know, which seems like a big deviation from a Gaussian. But this actually goes back even more interestingly, right? This goes back to an earlier work in 2001, I think. There was another paper. I don't know how many of you have heard about the Viola-Jones phase detector. So, right, so this one guy. So there's something called the Viola-Jones phase detector. Okay, now they had a paper in 2001 where they actually talked about something called an integral image. So these people actually know. So this group borrowed that idea, and they actually showed, and then they started from there in order to show various things.